Okay, so let's do page 9, charging by conduction and grounding. Grounding is the act of taking a charged object and making it turn neutral. So again, a little review. Electrons are negatively charged, protons are positively charged, protons are in the nucleus, electrons are outside the nucleus. We only move electrons. Negative charged object has more electrons than protons. A positive charged object has more protons than electrons. Perfect. Okay, number 2. A metal sphere is resting upon an insulating stand. A teacher holds a metal bar with an insulating handle. They specify this because if you're holding a metal bar and you touch another metal bar, you're going to probably get shocked, right? So you're just protecting yourself. The teacher uses the metal bar to charge the metal sphere by conduction. Which one of the... We already said conduction does not need friction. And if you don't know that, go to the previous videos. Conduction does not need friction because it wants to give away the electrons so quick. So this one would be an X because it's friction. You're rubbing the bar in the sphere. We don't need that. The teacher held the bar near the sphere and then touched the sphere with her hand. This is not Star Wars. We do not have the Force. You cannot touch something over here and then, like, it just doesn't work. The teacher charged the bar and then contacted it to the sphere. That's probably what would happen. Okay, number 3. Diagram A is the charging step. How does the sphere become charged? So we have 1, 2, 3, 4, 5. How many is that? 1, 2, 3, 4, 5, 6, 7. We have 7 electrons. The sphere becomes charged because do protons ever move? Protons never move. Ever. Ever. So we can take out this answer right away. Electrons move from the insulating stand into the sphere? No, the stand is just sitting there. So electrons move from the charged metal bar into the sphere. When the metal bar is pulled away in diagram B, the metal bar is, so if you're in my class, I might have steered you wrong because I said it was ambiguous. It's actually not. So we have 7 electrons here. I didn't realize that they were putting it like that. Then we have 5 electrons here. So we gave it 5 electrons. So how much will will the rod still have? It will still have 2. Because the law of conservation of charge, let's write that down. It says that if I give you 5 electrons, you gain 5 electrons. And vice versa, whatever, all the things. So if I started with 7, they need to be accounted for. So there's 2 and then there's 5. So when the metal bar is pulled away in diagram B, it's not neutral like I previously thought because we still have the 2 electrons over here. So it's still negatively charged but has fewer excess electrons than it previously did. C. Is C a insulator or a conductor? Look at your notes. Insulators clump up, remember? And conductors are evenly spaced out. So this would be a conductor. So why does the excess negative charge distribute itself in diagram C. So you can use the words conductor, evenly spaced, allow charge, and write incomplete sentences. Page 10. Here we have 6 protons Diagram A is the charging step. Can protons ever move? Protons never move. Never. So we can X this out and X this out. So electrons move from the sphere to the rod. So it seems like we gained 5 electrons, because this is now 5 positive, 5 protons more positive. Because protons don't move, the electrons are leaving to make it more positive. This is kind of a complicated concept, so I'm going to try to explain it to you in a different way. So if I'm neutral, I have a positive and a negative and a positive and a negative. That's neutral, right? Then if I have a positive and a negative, this is negative. So what happens if I give one of these electrons away? Then it becomes neutral again, right? What happens if I give both of these away? Then it's positive, net positive. Does that make sense? So the more electrons you give away, the more positive it becomes. So when the metal bar is pulled away in diagram B, we have 6 protons here, and we gained 5 electrons, so it's still net 1 positive. So it's still positively charged, but has fewer excess protons than it previously did. Okay. This, it starts as negative, it becomes neutral. This is positive, it becomes neutral. This is called grounding, where it's charged and then it becomes neutral. Polarization, you remember, is when we did the balloon and the wall, where it goes like this. So it'd be grounding. When the negatively charged sphere is touched, when this one is touched, blank move. Protons never move. Protons never move. So do electrons move from the sphere to the hand, or do they move from the hand to the sphere? If it's becoming neutral, the electrons will move from the sphere to the hand. Number 10. When the positively charged sphere is touched, blank moves. Protons never move. Ever. If we figured that out, we'd be geniuses and we'd be so rich. So if this is positive, how can we make it neutral? By adding electrons. We're adding electrons to make it neutral. So let me demonstrate. If I have something that's positive, 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 how many negatives would we need in order to make it neutral? We would need to add 4 electrons so that it's So it's 4 electrons and 4 protons. Right? So here we have to add electrons. We need to add 1, 2, 3, 4, 5 electrons in order to make it neutral. So electrons are moving from the hand to the sphere. Okay?